We've previously learned how to solve systems of equations by graphing. We can graph two linear equations, look at where the lines cross, and find the coordinates of that intersection. The intersection is what we call the solution to the system because it's the only point that lies on both of the lines. Today we want to level up that skill a little bit and learn to solve systems purely using algebra, not using any kind of graphing or visual means, but just by solving the equations together. We're going to focus today on solving by substituting a value from one equation into another. Our warm-up here has an example of that. So the first equation is simple. It has a single variable. And I have 3 apples that equals 30, meaning each apple is worth 10. In the second equation, there's 2 variables. So each equation can only solve for one variable, which is why a system of 2 equations can only have 2 variables, x and y. So in my second equation, I can't solve 2 variables at once, but since I already know that apples count for 10, then I know that the 2 banana bunches must count 4 each to make up the total of 18. So by substituting a known value, I can figure out an unknown value. That's kind of what we're going to be doing with solving by substitution. Before we do, I want to hop over to Desmos and look at our first example here. Y equals 3x and x plus y equals 4. Y equals 3x, x plus y equals 4. And I just want to point out I am using the unrestricted version of Desmos here so that I'm able to graph in standard form. If I weren't using it and I were using the star restricted version of Desmos, I would need to rearrange this and make it y equals negative x plus 4 or 4 minus x. And I would get the exact same line that I had when I graphed it in standard form. So the solution to this system is right here at 1, 3. If neither line is active, I can pick one of them here or pick one of them in the active equation window over here. And when I do, it highlights key points like intersections. So it tells us that the solution is 1, 3. But we want to figure that out, just like I said, without a graph. But I wanted to look at the graph because the basis of this method lies in the idea that we see in this graph, which is these two lines have the same output value of 3 wherever they meet. So when their output is equal, then we can find the the x value of the solution. So looking at this one, I want to kind of go over to the side here first, and then we'll go through the steps. So we're going to start off by going to y equals 3x, and we'll go ahead and rearrange this one into slope-intercept like what I had just done a minute ago. Y equals negative x plus 4. And these kind of systems you have solved in the past, probably as word problems, where it says, when will they be the same? So for this, we just basically are saying the y value is the same, so we drop the y's and we put the 3x equal to the negative x plus 4. This is a form of substitution where I'm saying that y is 3x, so I'm allowed to replace this y with this 3x. Now I have a single variable equation that I can solve, so I get 4x equals 4 and x equals 1. That's probably where you would have stopped the problem previously without actually finding the y value to say how much do they both have now that we know that it's at 1. So this is a problem where 2 people are saving money, when will they have the same amount? Or this thing is gaining and this thing is losing, when will they be equal? So we got the when, but then to figure out the how much, we need to plug that back in to one of our original equations. So we'll take the y equals 3x, but we'll replace x with the now known value of x, kind of like the apples from the warm-up example. So I get y is equal to 3. So our full solution to our system is 1 comma 3. One thing you always want to do when you're solving systems is we plugged into this equation, y equals 3x. So we want to use the other equation, y equals negative x plus 4, and substitute our solution to make sure that it's right. By checking it with both equations, we can be certain that we did everything correctly. So we're going to plug these in here, and that gives us 3 equals negative 1 plus 4. It definitely does. 3 equals 3. That's true, meaning that we've checked our solution and it is correct. So that's kind of the process we're looking at here. Now, the only difference from what you've done where it's y equals y is that we're introducing the idea that you don't have to have both equations solved for y in order to solve by substituting. So let's look at our steps here. Number 1, look for an equation that is solved for y or x. We'll put x or y alphabetically. If there is one, circle what x or y equals. So in our example here, we have y equals 3x. If there's not one, then we need to use inverse operations or algebra to solve one of them for a single variable. So we want to isolate one of the variables so that we can then substitute that into the other equation. So then we're going to substitute or plug in or replace the expression that we circled in the other equation for that variable. So let's see what that looks like. So I have x plus y is equal to 4. But I circled that y is the same as 3x. So I'm going to replace this y with 3x. And now my equation says x plus 3x is equal to 4. And that means 4x is equal to 4. Just like the work that we did over on the right side, but I didn't have to solve the second equation for y in order to do this. I just plugged in place the 3x where the y used to be. So this is kind of a both more simple and more elegant and advanced way of doing this. Rather than making both of them be in slope-intercept form, we only need to isolate the variable in one equation. So now we have an equation with only one variable, which we have already simplified to 4x equals 4. So the solution to that is x equals 1. It doesn't matter which variable we're solving for first, because we're going to have to solve for the other one afterwards. So we have x equals 1. We're going to substitute our answer from that step into either original equation, you get the idea. So let's pick the first one, which was y equals 3x. So we have y equals 3x, but we're going to substitute our value of x, 1. So now we have y equals 3. Then I'm going to add a step 4b, which is check with the other equation. And this really is an important step because it gives you that verification that you've done this correctly. So now that we know y is 3 and x is 1, just like we did over on the right, we're going to use the second equation, x plus y equals 4, and plug in the two numbers. So we're going to plug in 1 for x, 3 for y, and make sure we get a true statement. If we do, then we've checked our work and we're positive that 1 comma 3, the ordered pair 1, 3, where x is 1, y is 3, is our solution. So definitely include that step 4b to check after you use one equation to find your variables. Use the other one to check it. So we have some examples to practice here. I may point out a couple things. I'm not going to go through every one of them in detail because I want you to have opportunity to practice a few. On the first one, notice that y is already by itself. So this quantity here that y is equal to, we're going to substitute for y. The important difference on this one is that y has a coefficient, meaning we're going to have to distribute something. So let's rewrite this second equation, negative 3x. That part doesn't change. Minus 2, that part doesn't change. But now we come to y. Y is going to become, we put in parentheses, 5x minus 7, and then the rest equals negative 12 doesn't change. So the only part that changed, maybe we can highlight here, is we had y here, and we had this took its place. Otherwise, everything stayed just like it was. Now, since I have negative 2 times a binomial, which is 2 terms, I need to distribute like that, and I get negative 3x. The negative 2 times 5x gives me negative 10x. The negative 2 times negative 7 makes plus 14 equals negative 12. Now I have some like terms to collect on the left side. My two x terms have a total of negative 13x. I'm going to subtract 14 from both sides to get negative 26 on the right side. Then I'm going to divide by negative 13 to get x is equal to 2. Now that I have that, I'm going to plug it back into one of the equations. We'll just use the first one because it's already isolated, so that's usually the better choice. So we get y equals 5 times 2 minus 7. So that's 10 minus 7, meaning y is equal to 3. So now my proposed solution is 2, 3. And I'm going to use the other equation to check it. So negative 3 times my x value of 2 minus 2 times my y value of 3 equals negative 12. That's negative 6 minus 6 equals negative 12. Negative 12 equals negative 12. So I'm positive that 2, 3 is my correct answer. And then we move on to the next problem. So these first few all have a variable already isolated. It doesn't matter, again, whether it's x or y. It just matters that something is by itself, so whatever is on the other side of the equal sign can take its place. When we get to the third one, though, there's no variable that's already isolated. So what we look for is I look at my 4 variable terms, and I'm trying to find the one that will most easily solve for a single variable with a coefficient of 1. So this x is definitely my target here. So to solve for it, I need to add 2y to both sides and get x equals 2y plus 11. Now I can take this 2y plus 11 and substitute it for x in the first equation. That gives us negative 7 parentheses 2y plus 11 minus 2y equals negative 13. Need to make this pen smaller, it's driving me crazy. Okay, so distributing negative 7, I get negative 14y minus 77 minus 2y equals negative 13. I combine my like terms and get negative 16y, and then I add 77 to both sides. 77 minus 13 is 64. Dividing by negative 16, we find y equals negative 4. So notice that this time we solved for y first, and that's totally fine. It doesn't matter whether we solve for x first or y first. We then plug it back in to find the other one. As usual, we're going to plug it into here, which is the equation that was isolated for x. That makes it easy to find out what x is. So we get x equals 2 times negative 4 plus 11. That's negative 8 plus 11, so x is 3. So my proposed solution is 3, negative 4. I want to check that with the other equation. So negative 7 times 3 minus 2 times negative 4 equals negative 13. That's negative 21. And then negative times negative is plus 8 equals negative 13. Yes, that is correct. So, since I've checked with the other equation, I'm now very certain that, that 3 negative 4 is in fact the intersection. You can also double check these by graphing, of course, but the idea here is that we're moving beyond the need for graphs. So the fourth one is very similar. Again, look for the most easy to isolate variable, isolate that one, and then follow your normal steps. So that's kind of the idea. We've got, I think, let me see. We have both equations set to a variable, so this is the one we started with where we can just chain them together and basically say this goes here, so x plus 5 equals negative x plus 3. We've got ones where there's not anything pre-isolated, so we look for something that we can isolate, like this y or this y. And then we have one where there's already a variable isolated, so we just go ahead and plug that in for the variable in the other equation. So all of those are pretty straightforward and follow those same steps. We're going to look at a word problem now. So Hannah has $11.20 in a jar that contains only nickels and dimes. So important to know here is that nickels are $0.05, 5 cents, and dimes are double that. They're 0.10 or 10 cents. How many of each coin does Hannah have? So our two equations deal with, first thing is good to think about is what do the equations represent? So we have one equation about the value of her coins, 1120, and another equation about the amount of her coins, which is 140 coins. So one equation will set up how many coins she has. That's this one, n plus d equals 140, saying her total is 140 coins. The second one is about the value. That's where the 5 cents and 10 cents come in. So we have 5 cents times the number of nickels plus 10 cents times the number of dimes. And that is going to be equal to $11.20. Notice that in both equations, n represents the number of nickels. This 5 cents that we bring in here represents the value of each nickel, which is why it gets multiplied by how many nickels we have. But the n itself and the d represent the exact same thing in both equations, which is how many coins are there. So solving for a single one, I think the easiest thing would be to isolate n or d in this first equation. I'm going to choose to isolate d because then I'm plugging into this one that I'm multiplying by 0.1, which seems nicer than 0.05. So solve for a single variable. D equals 140 minus n, or negative n plus 140, same thing. So we've got that. Then we're going to substitute it into the other equation. So this 140 minus n will take the place, so I have 0.05 n, that stays the same, plus 0.1, and now I'm going to plug in this expression where d was. So 140 minus n, and then we have equals 11.2. So that's substituting that into the other equation. I'm just kind of doing everything in the same spot in this box. An easy way to get rid of fractions is to multiply by 10 or 100, or decimals, is to multiply by 10 or 100 to shift the decimal place over. In this case, I think we would multiply by 10, and then we would get 1/2 nickels, so 0.5 nickels, plus the 10 times the 0.1 here is going to cancel out. So that gets rid of that altogether. So we're just left with 140 minus n. A common mistake here is thinking that when I multiply by 10, the inside part of the parentheses also get multiplied by 10, so that this would become 1400 minus 10n. That doesn't happen, though, because remember that this whole part here is a single term within my equation. So when I multiplied it by 10, I'm not multiplying each piece of it by 10 because that would be multiplying by 10 multiple times. Instead, I took care of the 10 by canceling out this 1/10 or 0.1. So that equals, we multiplied 11.2 by 10, so that's 112. Now, if I want to get rid of this 1/2, I could multiply everything by 2. I think I'll go ahead and do that. So we get n plus 280 minus 2n is equal to 224. So now that the parentheses are not necessary, we're multiplying all 4 terms of the equation by 2. So now we're going to collect our terms on the right sides of the equation. I have negative n. I'm going to subtract 280. So I end up with 56 on that side, negative 56. Then we switch our signs, dividing by -1. So we find out there are 56 nickels. And then the easiest spot to find the quarters would be to plug back into the original equation, d equals 140 minus, and then substitute 56 for the nickels. So the number of dimes should be equal to 84. Now it would be best to check that using the other equation. So we would have 0.05 times 84. So 0.05 times 84 plus 0.1 times 140 minus 56. Oh wait, the original equation was just d for that. Let me not complicate things even more. 0.1 times d was 84, so I already messed up by putting the dime number where the nickels go. So let's erase 84 here and put 56 for the number of nickels like it was supposed to be, equals 11.2. So 0.5 times 56 is going to be 2, so that's half of 56, so 2.80, plus 0.1 times 84 is 8.4, equals 11.2. That's 10 plus 120, so yeah, that's 11.2 equals 11.2. That checks out. So our solution is 56 nickels and 84 dimes. So that's nickels and dimes. And there we go. So we can use this method with a variety of kinds of problems. So we saw 3 different cases here where we had a variable isolated, where we had a variable needing isolating manually, or where both things were already solved for the same variable. And then we saw a word problem. I'm going to leave these other 2 word problems, 3 word problems. I'm going to leave the other 3 word problems as practice for you to do, and you can check using the key on Canvas. But it's the same approach to solve them. Follow the same steps of isolating one variable if it's not already. Fortunately, in these, we have A is already isolated here, so this can plug in for A. Here, T is already isolated, so we can plug in 3P for T, and so on. So once we solve for one of the variables, plug it back into the other one, find everything you need. And that's pretty much it for today's notes. If you are confused on how to get these solutions, check on the keys on Canvas.